Welcome. We are looking at phase field modeling. We looked at one dimensional implementation for Cahn-Hilliard equation and Allen-Cahn equation. So, this lecture onwards we are actually going to discuss phase field modeling, that is with respect to microstructural evolution, how to write the equation, how to implement it and how to analyze the solution. So, this is what we want to do for the rest of this course. As a starting point, we want to do two classical problems. One is spinodal decomposition, the other one is order disorder transformation, where we want to look at the domain structure evolution. So, this is what we want to do in this lecture. To begin with, so let us look at what is involved in building a phase field model. So, you can consider these two cases where we are writing for spinodal decomposition and order disorder transformation, the domain structure evolution as prototype problems, and whatever is done in this problem is what needs to be done in every problem. So, the first thing that we want to do is to say that we are going to look at a system, we are looking at the microstructural evolution in a system. Let us consider the spinodal decomposition scenario. So, let me consider a system which is undergoing spinodal decomposition. So, what do I mean by that? So, we take a system. Initially, let us say that the composition is uniform everywhere, and so in terms of the phase diagram, so inside the miscibility gap, so there is a spinodal regime. So, I choose some alloy composition somewhere here. Okay. So, because and the temperature is like something like this. So, we start from here. So, the end compositions are also marked for us. So, the entire system is taken with this composition with some minor fluctuations. So, if you go across any line and if you look at composition, so the composition is something like this. Okay. So, this is some C naught, the overall alloy composition, this is the position and this is the fluctuation. And how is this system is going to evolve is what we want to look at. So, first decision that we want to make whenever we are writing a phase field model is to decide what is going to be the order parameter. Okay. So, that is the order parameter is the one that is describing the microstructure in the system. Okay. So, step 1 in phase field modeling is identify the order parameter. So, in the first case we are identifying the order parameter to be composition. This is the case that we are considering now. Once we identify the order parameter, which is basically used to describe. So, what is the purpose of this order parameter? Order parameter is nothing but a description of microstructure. So, wherever order parameter, namely the composition, becomes this value, that is going to be the alpha phase, and wherever it is going to be this value, that is going to be beta phase, and so on. So, we are going to describe the microstructure using an order parameter, that is the first step. The second step is the thermodynamics. So, what do we mean by that? We want to write the free energy functional in this case, functional, because it is a functional, because the free energy is a function of composition and gradients in composition. Okay. So, this is the approximation we are making. It could be higher order gradients, as we saw in the derivation of the Cahn-Hilliard equation. It is possible to take higher order derivatives. We will probably look at one of those cases later in this course, but for beginning we want to take a free energy functional, and the free energy is a functional, that is in terms of the order parameter and its gradients it is written. This basically describes the thermodynamics. This basically describes that my free energy versus composition, the free energy versus composition has a double well, and there is energy associated with the interface region where the composition changes and things like that, and that it leads to this kind of phase diagram is all built into the free energy function. So, first is the geometric description. Description of microstructure is basically the geometry or the topology, and the second is a description of the thermodynamics of the system. Okay. Now, the order parameter that we have identified is a conserved order parameter, because composition, the integral of composition over the volume, if you take with time how it changes, that is 0, because integral C dV is some C naught, it is a constant. So, d by dt C naught is equal to 0. So, we have the description of microstructure, we have the thermodynamic description for the given microstructure. The step 3 is to actually write down the phase field equation. So, in step 2, so let us write it in a little bit more of detail. So, G of G by NV, let me say, is we have chosen to be F0 of C plus kappa del C squared, so dV. So, this is the simplest that we can think of, where F0 of C is a function like AC squared into 1 minus C whole squared. So, I now have a description of the thermodynamics. Now, the step 3 is to write the evolution equation. Because C is a conserved order parameter, we want to write the Kohn-Hilliard equation. What is the Kohn-Hilliard equation? It says dou C by dou T is equal to, so I am going to assume the mobility is a constant m del squared acting on mu, which is nothing but del G by NV by del C, because this is nothing but the mu, the chemical potential. So, that gives me m del squared, and del mu G by del C, the mu is nothing but the Euler-Lagrange equation. So, that is nothing but dou F0 by dou C minus 2 kappa del squared C. Okay. Now, let us call dou F0 by dou C as some function G of C. Okay. So, now we have the evolution equation, which is given by dou C by dou T is equal to m del squared acting on G of C minus 2 kappa m del power 4 C. Okay. So, this is the third step. Now, the fourth step is of course solving this equation. So, step 4, this is what we want to do now. We have already done it in one dimensional case, we now want to do it in a 2D case. Okay. So, let us take what is involved in solving this equation in 2 dimensions. Okay. So, del squared in 2 dimension is nothing but del squared by dou x squared plus del squared by dou y squared. So, already this is a second derivative, which means it involves points to the left and to the right of a given point. So, you can evaluate G at every point in my domain, right. I have this domain. So, I am going to split it into lots of points, and at every point I know. So, I can get on the left, right and top and bottom for the y. So, that is possible. In addition, when you have del power 4 C terms, it is del squared whole squared. So, it has del power 4 by del x power 4, del power 4 by del y power 4 plus del squared by del x squared, del squared by del y squared. In other words, it is going to have these cross terms also, and it is a fourth derivative which already involves points to the left and left of left, right and to the right of right, top and above top, and bottom and below bottom, and so on and so forth. And del power 4 in addition is also going to have these cross terms. So, in other words, doing a finite difference implementation of this is going to be very involved, but we are going to do a Fourier spectral implementation. So, semi implicit Fourier spectral implementation. In that implementation, as we have discussed earlier, the periodic boundary condition is implicitly assumed. So, periodic boundary condition means that there are no surfaces that we consider. So, all points have points to the left, right, top, bottom for that matter, right. So, even this point has points to the right, which are nothing but the points here. Even this point has points to the left, which are nothing but these points, and so also the top and bottom points. So, these points have points to the top which are these points, and these points have points to the bottom which are these points. So, that is how the periodic boundary condition works. So, there are basically no surface points. Okay. Now, that is implying when we do the periodic boundary condition implementation, what it means is that we are assuming that the microstructure that we are considering is a representative volume element or VE. That is, this region that we are looking is a representative area of the entire microstructure. So, whatever is happening here, if we look at, that is sufficient to get the complete information about the microstructure. So, that is an implicit assumption that is made if you are using periodic boundary condition. And because we are looking at microstructures, and this is true even when you look at experimentally the micrographs, what we are looking at is some portion of the microstructure. We are assuming that the portion we have chosen is representative of the entire surface, and that is how we make our analysis based on these small regions that we look at under a microscope. So, we are going to assume that this is given to us. Assuming that, then you can do a Fourier transform based implementation. So, that means dou C tilde by dou t is nothing but m. So, it will become, now we are doing it in 2D. So, the del squared will have the kx part and ky part. So, we are going to have minus, so kx squared plus ky squared acting on g tilde minus 2 kappa m. So, minus k squared and another minus k squared. So, this is going to give a k power 4. So, that is basically k x squared plus k y squared whole squared acting on C tilde. Okay. We are also going to assume that kappa m a everything to be 1 as usual, but for now let us say that this is at time t plus delta t and this is at time t. Okay. So, then that gives C tilde at time t plus delta t is nothing but this quantity is going to come 1 plus 2 kappa m k x squared plus k y squared whole squared multiplying delta t. So, that is going to come is equal to C tilde at time t minus m k x squared plus k y squared delta t g tilde. So, C tilde t plus delta t is going to be C tilde t minus m k x squared plus k y squared delta t g tilde divided by 1 plus 2 kappa m k x squared plus k y squared whole squared delta t. So, this implementation wise you can see. So, this is the final step. Now, we are going to go to the computer and solve this problem. Implementation wise you can see that this is no different from the 1D implementation, except for in addition to kx now we have ky that is added. Okay. So, this is what we want to implement now, and we want to write a script in Octave which will solve this problem. So, let us do that and look at how the solution looks in 2D. In 3D also it is a straightforward generalization. So, in addition to kx and ky you will have kz in 3 dimensions. So, that is all that is there in 3D, but because of the computational resources that will be available to us, I would like to do everything on a laptop, and that is not possible if you want to do 3D simulation. So, I am going to restrict myself to 2D simulations, except for this additional complexity. There is nothing new that we have to deal with when we do 3D simulations. So, if you understand this, you should be able to do 3D simulations also fairly comfortably. Okay. So, let us try to implement this problem now. So, let us go to the computer as usual. So, I need to check that I am in the right directory. So, I am in the right directory. So, I let us call this as 2D Conhilliard FFT dot OCT. So, that is what I call the program. So, first thing is clear all CLC, CLF. So, I clear everything that is already there. I am also going to introduce this command called more of. The purpose of this command is that when we want to plot things and unlike 1D, those were just profiles, so you can keep on the same plot, but now we are going to look at microstructures. So the microstructures are going to evolve, so we want to get a movie kind of feel. If I do not put more of the entire script is executed and then all the figures are shown one after another, which is not what I want. I want to see the microstructure as it is developing. To do that, if you put more of, then what it will do is that it will show the figure, it will do the next computation, it will show the figure corresponding to that, and so on and so forth. Okay, so this is just to get you proper microstructure as the system is evolving. To see that, I have put more of. Okay. So now what we are going to do, of course we want to start with an initial profile. So let us say that we have total say some 64 points. Now here it is possible, because now we have to say nx and ny, right, because there are two points, because the x and y, if you have z, nz also you have to say. So let us say that I take a square domain, the region where I am going to evolve my microstructure. So it has nx is 64, ny is 64. So now we have to start an initial profile, and the initial profile is going to be a noisy profile. So I am going to take some average composition, I am going to pick it up as 0.5, because that is where the unstable region is, and I am going to put some small noise about 0.5 plus or minus some small noise. So that is what we want to do. So let us do that. So you say for I is equal to 1 to nx, for j is equal to 1 to ny. What do we want to do? We want to define C of I comma j. So I am going to define composition as what? 0.5 plus or minus I want to do. So I am going to take this 0.5 minus rand. Okay. So now the rand function is going to return a random number between 0 and 1. So if you subtract it from 0.5, you will get either a positive number or a negative number, which is of the order of 0.5. So I want to multiply it by the small number, which is nothing but the noise. So now this will be 0.5 plus or minus some number which is of the order of 0.05. Okay, so that is going to be the initial composition profile. So that is the reason why we have put it like this, end for and end for. So this is the initial profile. So we want to plot and see. Now this is a 2D information, so it is going to be a 3D plot. So I am going to plot it as mesh C. Okay. View 2 is to look at this mesh from the top. I will show you how it looks, and then so let us just run this part of the code and see how it evolves. So let me see if I am in the right directory. So I say octave, and then I say source 2D. Okay. So you can see that this is the microstructure I get, and these colors basically tell you what is the value. So it's more or less all the colors that you see, which means and you can see it is a 64 by 64 system. So what we have done is to look at the projection. So if I actually want to show you how the microstructure itself looks, you can see. So I have taken about 0.5 the noisy profile, right. So it's all compositions which are about 0.5, but with some noise. So that is what it is, and when we take this view 2, basically we are looking at top down, right. So that is basically how it looks like. Now this is the microstructure that is going to evolve. Okay. So let us go back and let us introduce another command called pause 0. Pause 0 means after showing this figure, it will stop for 0 seconds and then it will move on to the next figure which it has to plot. Okay. So pause 1 for example will wait for 1 second, and if you just give pause without any comment, without any number, it will wait till you give some keyboard input before it moves on to the next figure. So let us put pause 0, and try to evolve the system. So, what does evolving the system involve? Evolving the system would involve calculating the G and taking its Fourier transform, say taking Fourier transform of C and so on and so forth. So, let us do that for I is equal to 1 to m, okay. That is the time step, but I also want to plot it once in some number of steps. So, let us say 1 to 10 for let us not call it I, let us call m 1 to 10, n is equal to 1 to 8. Okay. So, end for and end for. Now, the n 1 to 8 is the inner time loop. After this is over, I am going to plot this composition every time, right, and pause 0. So, every 8 time steps once this is going to be plotted. So, that is what this inner loop for, and like that it is going to go 10 steps. So, total number of time steps is going to go is 80. So, the final end for is meant for that part, and we want to also define dt. So, let me define dt to be equal to some 0.5. Okay. We also want to define half nx is equal to nx by 2. These are needed because we want to implement periodic boundary condition. Half ny is equal to ny by 2, okay, and del kx is equal to 2 pi by nx, and del ky is nothing but 2 pi by ny, right. So, we want to have all this defined. Previously we just defined half n and del k, but now because there is x and y, you need to define them both. Once we have done that, so let us calculate in the inner loop. First we want to calculate g. What is g? 2 times a. So, let us also define these quantities. Let me call a is equal to 1, m is equal to 1, kappa is equal to 1. Okay. So, 2 times a dot star c dot star 1 dot minus c dot star 1 dot minus 2 dot star c. So, it is 2 a c 1 minus c into 1 minus 2 c. So, that is what g is. So, we calculate g and then we take the Fourier transform. So, g hat is nothing but f of t 2 of g. So, f of t 2 is to indicate that it is a 2 dimensional Fourier transform. Okay. So, c hat is nothing but f of t 2 of c. Okay. So, now we have the Fourier transform done. Now, what we are going to do? So, we are going to say for I is equal to 1 to nx, for j is equal to 1 to ny, right. So, we want to implement the periodic boundary condition. So, this is end for, this is end for. So, these end fors are for the for loops for the nx and ny. So, first we want to do this. So, we want to say if I is less than or equal to, right, less than or equal to. So, I minus 1, I minus 1 is less than or equal to half nx, then kx is equal to I minus 1 into del kx, right. So, that is what we defined, and if I minus 1 is greater than half nx, so then kx is going to be I minus 1 minus nx into del kx, right, and end f. Okay. So, we are going to repeat the same thing for the while loop also. So, let me take the 4. Okay. So, j minus 1 is less than y, then k y is equal to j minus 1 times del k y. In this case del k y, del k x, they are all the same, but I am writing it generic enough so that it can be used in the other cases also, right. So, it is not necessary that n x and n y are the same, it is not necessary that the delta k x and delta k y are the same, and so on and so forth. So, I am writing for that generic case. So, now we have implemented periodic boundary condition and for both x and y. So, we want to define k squared as k x into k x plus k y into k y. And now, we want to define k power 4 as k squared into k square. Okay. So, now we are ready to evolve the system. So, we say that c hat of I comma j is nothing but c hat of I comma j. So, c hat of I comma j minus dt times k 2 times h hat m times dt times k 2 times g hat of I comma j, right, I comma j. So, that is the entire thing. Now, divided by 1 plus 2 into m into kappa into k power 4 into dt, right. So, this is what the new c hat is. So, you evolve it. Now, we have to take c to the real space, because c is equal to real of inverse first Fourier transform of 2D of c hat. Okay. So, we take it real and that ends the loop. So, then we plot and we pause and then we keep doing it. So, this is the complete loop. Now, let us so, we have the entire code now ready. So, let us try to run it and see what happens. Okay. So, let us source. So, I get yes. So, as you can see, the microstructure is evolving. Okay. So, you get all these red regions, you get all these blue regions, and they correspond to A and B rich regions. Okay. As you can see, the microstructure is coarsening. So, the system has come out. So, let us do it once more, so that we can look at the evolution from the beginning. So, let me have this okay. Okay. So, this is from very early stage. We can see whatever was all colors is slowly becoming phase separated into regions which are rich in A and rich in B, and the random number that is different every time. So, that is why every time you run a simulation you get a different kind of microstructure. If you want to get the same microstructure, then you have to use a seed, and using the seed same random number sequence can be generated on the computer. Okay. So, the evolution is quite fast here. So, let me do one more thing. So, let us say that we start and we go to the same 10 steps, but let us plot the microstructure once in 20 steps. Okay. So, let me evolve. And so, this is what it is, and this is the initial microstructure. Within some 20 steps you can see it became that, and another 20 steps. So, it is becoming so you can see all A rich regions and B rich regions forming, and it is evolving, because we are now going to longer time. So, you can see that these are coalescing. So, here at this point they are all coalescing. And this is becoming 1, and this is probably going to become 1 together. So, you have this interpenetrating microstructure that is coming up, that is very very typical of spinodal decomposition. Now, let us take a look at, so this is just a projection, I am looking from the top. Let us take a look at how the microstructure itself looks like. So, this is how the microstructure looks. Okay. So, the microstructure goes from 0 to 1. So, there are regions where it is all 1, that is basically the B rich region, which is seen as a red patch, and there are regions where it is the blue regions that you see, all these valleys that you see are basically where the composition is 0. So, the entire microstructure consists of composition regions where it is 0 and composition regions where it is 1, and there is this effect of the interface on the composition part. So, which we will see clearly when we look at the simpler precipitate growth case. So, this is the microstructure, we are looking top down, and that is why it looks like this. Okay. So, in this figure, whatever is all blue is basically A rich, all red is basically B rich, and you can see that the interface is a region where it goes from red to blue. So, this is basically spinodal decomposition modeled using the phase field equation, namely the Conn-Hilliard equation, and implemented using a semi implicit Fourier spectral technique. So, we start with a microstructure which is about 0.5 with some noise, and it evolves to give you A rich and B rich regions, and A rich B rich regions have this typical microstructure, which is what you would see if you did look at a spinodally decomposed microstructure. Okay. So, this is the first part. Now, we want to do the same thing, 2-dimensional implementation for the Allen-Conn equation. We will do it next in this lecture. Thank you.